The last real lecture, okay, and we're going to finish the collaborative pattern, and I'll clarify a few more things about how these atomic-based systems work and how people actually implement these global barriers, right? So there's there are a couple of things that you really need to understand to be able to use these persistent thread kind of techniques well. And then I'm going to check on you guys about the project. So I want to make sure that we have a little bit of time to discuss any issues about the project. So starting Thursday, we're going to have just the clinic, so that you can sign up for some time. I think some of you already did with Carl last week, right, on Thursday. How many of you talked to Carl about the project last Thursday? Good, good. Yeah, so so this Thursday, I'll make some time available from me, because I think Carl is actually in India, right?
Yeah.
Yeah, so I'm going to be the one who will be doing the clinic on Thursday. So we'll do a little bit sign up sheet, so that each group will talk to me for about 15 minutes. Okay, so and go from there. And you don't have to come and talk to me or Carl every week, but you should talk to one of us at least once every other week, right? And so make sure that you're on track. Okay. So let's and also Mert is going to be here. Is Mert here yet? Okay. So we will figure out exactly what's going to happen to the last MP. Okay, and it's overdue, but I think he's also trying to submit a paper, so that's why things are clogged up a little bit. But I think he should be there already. So let's go back to the collaborative pattern. So we're talking about BFS, right? So from in the original lecture, when we talk about breadth-first search, we said, okay, in every iteration, we generate a frontier. And if the frontier is small enough, then we can use a small kernel. And the small kernel basically uses sync threads in the inside a thread block, because if the frontiers are small enough, all you have to do is just use one thread block, and there are enough threads to process the frontier, right, and generate a new frontier. So as long as the frontier fits into the shared memory, you should be able to just use one thread block. And the fact that you don't need to read write from the global memory, and you can use sync threads rather than terminating the kernel and then relaunch the kernel, you should be able to get much better performance, and we're going to see those numbers. But as soon as the frontier grows too big for the shared memory, that's when you'll be forced to go into the global memory. And once you go into the global memory, you may as well use more thread blocks so that you have more threads. Right? You have bigger frontier, you have more threads to participate, you generate bigger frontiers, and then so all this works. So that's why we have this kernel 1 and kernel 2. However, switching between the kernels is kind of a pain, and for code maintenance and so on. So a lot of times people don't like that. So most people, when they write libraries for this kind of application, they tend to use persistent thread blocks, so that you can eliminate at least the kernel launch overhead. Okay, and so the kernel is going to be running continuously, and then there will be some kind of synchronization that emulates the effect of terminating the kernel and then relaunch the kernel. Remember, the way to terminate the kernel and then relaunch the kernel is because you have these different thread blocks that are making progress independently, right? So when you terminate the kernel, you make sure that all the thread blocks have reached a certain point, and then you relaunch them so that they can start from the same point. And that's barrier synchronization. So what you're really trying to do is to have a barrier synchronization, and then you force everyone to be able to to be at the same point, and then everyone can see the results for everyone else, right, in the previous iteration, and then before they go into the next iteration. So we're going to talk about atomic-based block synchronization or atomic-based barrier synchronization that force all the thread blocks to be at the same point of execution before they can all continue, right, to the next phase. So essentially at the end of every iteration, or at the end of the creation of the next thread block, frontier, then you do a barrier synchronization. And make sure that all the threads have indeed finished generating the next frontier and it's clean. And then you release everyone from the thread, from the barrier, so that they can all go and pick up the frontier nodes and then start to generate the next frontier, right? So this is what we're going to talk about now. And unfortunately, the problem, it doesn't really solve the problem of very small frontiers, because if you have very small frontiers, you can actually, you should be able to just use one thread block and use the shared memory for that. So this is not going to be the topic that we discuss. However, there's no reason why when you use persistent kernel, there's no reason why you cannot use specialized code in the persistent kernel and only activate one of the thread blocks when you have very small frontier. So the kernel code could just say, test the size of the frontier, and if the frontier is small enough, all the other threads beyond the thread block 0 will just turn them off, because you can just use if then else statement. So that's the reason why I'm not going to explicitly talk about it, because you can actually build the equivalent of a smaller kernel with if then else statements in your persistent kernel code. Okay, so I'm going to be mostly focused on how you build that persistent kernel and how you synchronize the thread blocks. Okay. Now, so let's go back to how we can combine kernel 1 and kernel 2 into a persistent kernel. So we launch the blocks by we launch a fixed number of blocks, and the fixed number of blocks is the number of SMs times the number of maximal blocks per SM. So this is actually this is actually one of the things that you need to be careful about, because when you have a persistent kernel, you need to make sure that all the thread blocks are truly running on the SMs all the time. The reason is, if one of the thread blocks is not really running, and then you reach the barrier, then everyone else is waiting on the barrier, right? Everyone else is waiting on the barrier. And the barrier is going to be implemented with a while loop, okay, of these threads. So as far as all the threads are concerned, they are all running while loop in the SM, okay, in the SM, waiting, right? But if one of the thread blocks somehow cannot be scheduled into the SM, somehow cannot be active in the SM, it will never arrive to join the barrier, right? So everyone else will be busy waiting on the barrier, and this guy never shows up, and you'll have a deadlock. You'll never be able to get out of the barrier. So you have to make sure that all the thread blocks always will be able to run on the SM all the time. So that's why you can only launch the number of SMs times the maximum number of blocks per SM, so that you will be able to always accommodate all the thread blocks, all the active thread blocks in the SMs. But this is easier said than done, because the maximum number of thread blocks actually depends on your occupancy. So if your kernel takes too much resource, you may only be able to run 1 or 2 thread blocks per SM. If your kernel does not require much resource, you may be able to run up to 8, right? Or even more thread blocks. So this is actually codependent, okay? So you need to be careful, not to over generate, blocks. Then you start to have deadlocks. So every generation of hardware will have different number of SMs and also the number amount of resources available to the thread blocks. So you need to do the explicit calculation. This is the reason why persistent kernels are not for the faint of heart. Okay, persistent kernels need to be designed extremely carefully so that you will not you will not cause deadlocks, and also if you be conservative, you will not end up underutilizing or dramatically underutilizing the resources, right? So you need to be aggressive enough, but you also need to make sure that you don't accidentally cause deadlocks. So this is something that as we often say, don't do this at home, okay? Unless you're a trained professional and then really know what you're doing after you finish 508, and then you have very, very high confidence that you know how to craft these kernels and then know the resource requirements. So I'm going to just go right into the code. We already talked a little bit about this last time, right? So so hopefully this time it would make a lot more sense. So the GPU kernel that all these thread blocks will be running will look like this. So you come into the kernel and you generate a global ID. So for your essentially it's your global thread ID for the thread, right? So among all the threads in the grid, there will be a unique ID for everyone, right? So this is the global ID, and then we're going to see how the global ID will be used. And then you have this big for loop, and the for loop is about keep generating the frontiers. In every iteration of the for loop, you're going to be generating one frontier, right? And then the next iteration, you will consume the frontier and generate a new frontier until you exhausted all the nodes. You visited all the nodes, and then you can no longer generate any new frontier. And that's when you're done, right? So this is the classic breadth first search. So this while loop will iterate, and every iteration of the while loop will be one iteration on the one frontier iteration, right? So you will see that I'm going to visit the neighbor. So I'm going to come in and I start the frontier with the single source node, right? The source node is the first frontier, and then you go and visit the neighbors of the source node, and you queue all the output, all the neighbors into the output queue. And so now you have the next frontier. So after you finish this one, you have the next frontier in place, and then you update the frontier size, and then you do a global barrier, right? So this is when you need to make sure that all the threads wait here, and then some of the threads may be still executing this for loop, right? You have to really visualize how the execution works, because all the threads are going to be doing this for loop, but they're going to be taking different parts of the frontier and then generate, insert the neighbor nodes of the frontier nodes into the output queue, right? So that's, all of them are going to be making progress in different rates and different phases. So some of them will reach the barrier first, and some of them will not reach the barrier later, right? So that's why after everyone reaches this point, that's when you know that you have exhausted the current frontier, you have generated the next frontier in the output queue, and you are now ready to release everyone into the next iteration, and they will go into the new frontier, right, and process. Make sense? Okay. So now that we understand this, we're going to go into the global barrier and then look at how it's implemented. There's multiple ways you can do this, but this is one of the most common way that people implement a global barrier. So basically, we start with the we have two global variables. One is the thread end, and then the other one is thread run. So these two variables are going to be operated on by the atomic operations, and together these two will implement a barrier, what I call the lock gate. Have you seen, in Panama Canal, you have these ships that you have these water locks, right? So the ship will come in, and then you close the gate, you open the gate, and then the ship will move forward, then you close the gate, open the gate. And this is how you can actually get the ship to go up, right, against the water, right, against the running river dam. So there, we're going to be having essentially a water lock in the front and in the back with this, a global barrier. So we're going to have a variable called frontier. And this frontier is going to be a local variable. Okay, it's a variable that is going to be in every thread. So it's a private variable. And this variable indicates what this particular thread is working on. Which iteration of that frontier while loop that the current thread is working on. Because some of the threads may be still working on the frontier when some of the threads already finished with the current frontier. So those ones would finish with the current frontier and say, oh, I'm waiting to do the next frontier. Okay. On the other hand, the threads that are still working on the current frontier will say, I'm working on the current frontier. So every thread will have a local frontier variable that indicates where the thread is. Okay. And so we have those three variables, two global variables and one local variable. So this piece of code is at the bottom of the previous slide. Okay. So after a thread finishes with the for loop, right? The for loop that essentially it has finished all the duties on the current frontier, and the thread says, I'm done here. Okay, I'm done here. I'm out. So then the thread will increment the frontier, the local frontier variable by 1, and say, I'm ready for the next frontier now. Okay. But some of the threads will be still working on that in that for loop, right? Working on their portions of the current frontier. So their frontier value will be still stuck at the previous frontier value, right? So this is why it's a local variable. Each thread could be either the current one or the next one. So it depends on their progress. So this is the local iteration counter. By the way, I'm going to upload this version of the slide because I actually didn't like the comments. I'm not naming names, but one of my former students wrote the slide, and what he wrote was perfectly correct, but it's not exactly intuitive. So I changed the comments so that they will become more intuitive. So when you go home and study, it will make more sense. Okay, so the frontier is the local variable. Iteration counter, which iteration the local thread is working on. So it's either the frontier that you just finished, where you're still finishing, or the frontier that you expect to work on because you finished the previous frontier. Okay. Now, so the TID is the thread ID. So this is the block. This is within the block. Okay, so this is the thread ID within the block. Okay, so that's why it's thread ID x.x. So when we say TID is equal to 0, that means that we're using the head thread, the thread 0 of every thread block. So all the threads zeros in all the thread blocks will execute this piece of code. Right? So only one thread in every thread block will execute this piece of code. It will do an atomic add to the thread's end. So this is really just saying that my thread block has completed the execution. Okay, so only T0 would do this would do this particular action. So that basically when the thread block finishes with the work, only one thread will say, okay, another thread block is done, right? Another thread block is done. So this signals that the number of threads finished the current iteration has just increased by 1. And you want to see all the thread blocks to report to this, right? So this is the point of the barrier. You want to make sure that everyone has arrived before you let people go move on. So the thread block comes down here. You say, okay, I'm done. So increment that value by 1. And then after you increment this, and then there's a single thread in the entire grid, right? This is the true 0 thread in the entire grid, right? That thread 0 of the grid is going to come and say, I'm going to wait. I'm going to wait until I have enough thread blocks that all reported to the barrier. So it's going to keep testing whether the thread's end variable is equal to the grid dim. Because once you reach the grid dim, you know that all the thread blocks have reported, right? This is you're waiting for all the thread blocks, right? Which is the side, the grid dim.x, to report to that thread grid. So the way that you should think about this is that when the thread blocks complete their work, right? When the threads complete their work, the thread blocks come in and say, "Oh, I'm done." So you increment the counter, but then they move on into a thread sync thread barrier down here, but only but you have a single thread which is thread block 0 that's going to be continuing to test whether everyone has reported. Right? And this busy testing is only done by one of the threads. Okay? And that thread is going to just keep doing this until the value is grid dim, and then you will exit the while loop. Well, so one of those threads will not finish this until it actually see that all the thread blocks have gone through this. Okay? And then you will have you'll have a kind of two atomic operations. One is to say, I'm done with the barrier, right? I'm exiting the barrier, so I'm going to reset this in preparation for the next round, okay? For the next iteration. So I'm going to reset the PTR thread's end, and this means that it's prepared for the next barrier waiting, right? So it's reset so that we can be prepared for the next round of barrier reporting, right? So this is setting up for the next iteration, and then you will increase the PTR threads run. So this is actually an unfortunate name for the variable. It's really the official, what I call the official iteration number. So when this thread 0 knows that everyone has completed the work, you will officially increment this variable so that it will give you the iteration number for all the threads to work on in the next iteration. So it will be increased only once per iteration, only by one thread. So it's only incremented once per iteration. So it gives you the official current iteration count that everyone has completed. Okay? Yes?
If only thread 0 can access that PTR thread from, why making it atomic?
Okay, this is a great question. The reason is this. The reason is, remember, PTR thread run is actually, one of the, this is the official iteration indicator. Okay, so it should be readable by all the, all the threads. So using atomic operation is not because of the race condition here, as you correctly pointed out. There's only one thread that will do it. But if you use atomic operation, it will force the value to become visible to all the other threads. Otherwise, remember, in global memory accesses, if one of the threads write into global variable, global memory content before the kernel terminates, that value will not be visible to other thread blocks, right? So this is forcing the consistency, so that all the other threads will see the value. Does that make sense? Okay. So with this, then if the thread ID for all the other thread blocks, the ID here, the global ID. Remember, this guy is already added one to the to the thread run, right? So all the other thread blocks will actually do a essentially this is just a read. So because it's atomic add with 0, so this is really just reading that value. Okay. So this is going back to this comment. If you use atomic operation, the value that you write will be forced out. And then also, if you do a read, you will be forced to read the latest value, right? So this is the GPU way of keeping the memory value, to make the memory value correctly readable by other threads, and you read the correct value updated by other threads. So you read this value, and then compare that value with your frontier, okay? With your frontier. And so basically, you say, as a thread, okay, as a thread, this is the head thread for every thread block, right? So as the head thread of every thread block, I'm going to be here. I know that I'm done with the frontier, okay? I'm done with the previous frontier. So I already incremented my frontier count. But not everyone else have done that yet. So I'm going to be waiting here, okay, waiting here, until everyone else has finished their work. And then the single head node for the entire grid has completed the iteration and incremented that run. So this thing will become the same value as this thing. Okay? When this variable has incremented, then it will catch up, right? It will catch up to the frontier of those nodes, of all those threads that have already reached this point. And then, so it will be equal at this point, and then the head thread, so all the head threads of the thread blocks will come out of this particular while loop, right? So we have multiple while loops here. The single global thread will be stuck in this while loop until everyone else has reported. And then you would increase this value so that the official iteration count will match the local iteration count of all the guys waiting for here. And you would reset the value so that the barrier value so that it's ready for the next round. And here, everyone else, all the other head thread blocks will be waiting in this while loop, will be repeating this while loop until this guy officially says, the head loop officially says, I'm advancing the iteration count. Okay, everyone truly that's done. And then all the rest of the threads. Remember, I only talk about the single head thread of the entire grid, right? And also the head threads of every thread block. So what happens to the other threads? The other threads, after they're done, they will be coming down to the sync threads. Okay, they're coming down to the sync threads. So they're all waiting here. And except for those head threads. And those head threads will be stuck here until they're satisfied. So this guy will release the rest of the head threads. And then all the other threads, all the head threads will come down to the sync threads. And only after all these threads join the sync threads, all the threads will be waiting in the sync thread barrier of their own thread block, right? So all of them will be waiting there. And when all the other threads come down, they will come into the sync thread. So the sync thread barriers of every thread block will independently be released as these head threads come out of the while loop, right? Each of these head threads coming out of the while loop will release one of those sync threads in the thread block, right? So, but that's okay, because the only reason why they can leave this barrier is because everyone else has already reached this point. So then you can independently release all the sync thread barriers of individual thread blocks. Okay, it's a little bit conservative, but it guarantees that everyone truly has reached this point. And then, this is sometimes we call the two-phase barrier. Okay, and if you have MPI code and so on, that you want to have a real barrier. So this is the MPI collective barrier. The implementation would look something similar to this. Okay. Couple other things. One is, you say, okay, what if I have some kind of a weird situation where, within a thread block, some of the threads, may be finishing. Let's say some of the threads may finish after, right? May finish after the head thread, right? It's possible. So let's use that scenario. And so if I have a thread block and the head thread is not, the head thread is done first, and then the rest of the thread block somehow reach this point later, right? It's possible. So the head thread is going to come in, and then increment this thread end, so that as far as the rest of the head threads are concerned, that thread block is already done, right? You said, wait a minute, but some of the threads in the thread block are not done yet, right? So this is a potential problem. So let's see how it plays out. So the head thread is going to come down, and then the head thread eventually will also, they'll reach this point, right? Reach this point and see if all the other head threads are done. So let's say, for some reason, the rest of the thread block was delayed so much that all the other head threads also have reached this point, right? So then all the head threads will be released into this point, right? So at that point, the head threads will be stuck in the sync threads, because they'll be stuck in their per thread block barrier until the rest of that thread block arrives, right? So this guarantees that the thread block will not be released until the entire thread block have indeed completed. So this is the complexity. Okay, this is the complexity of these kind of global barriers. When you have these partial barriers, like the thread block barrier, right, and the sync threads, they only guarantee the barrier semantic within the thread block. So now you want to implement a global barrier that can be used to synchronize all the threads and all the thread blocks. So how do you use these partial pieces of thread block level barrier to be able to ensure that everyone has indeed completed? So you really have to design all your while loops and waits and so on to make sure that every scenario, right, in every scenario possible, you will have, always have the correct barrier semantic. Okay, and this is usually done with some kind of a proof that you need to actually go and prove that that you can indeed handle every possible case scenario correctly. Any questions about that? Yes.
So the pointer threads run and pointer threads end are in global memory, right?
You mean this thing?
Yeah.
Yeah, this is in global memory because these variables need to be visible by all the thread blocks.
So at the beginning, you could theoretically just have the global representative or whatever set it to 0, right?
Oh yeah. That's exactly what it is. So that's why here this is the global representative setting to 0 in preparation for the next one, right? For the next iteration. So before you go into the first iteration, you also need to have a global thread representative to set it to 0.
So like at the top of this code, you only need the global one to do the atomic operations.
Yeah. This thing should be the global. Yeah, that thing should be the global only one. Yeah. Okay. Anything else? Very good. So this is probably the last major kind kind of concept that I want to make sure that you walk away with from this from this class. So then you have pretty much all the important pieces. So let's take a look at some of these things. There's some interesting observations. One is when we this is the profile for a breadth first search on one of the graphs, and then so these are the kind of the histogram, the average execution time of the histogram of, let's say, the first 100 frontiers, and then the next 100 frontiers, and so on, until you're done, right? So every 100 frontier, because this is a very small, these are small frontiers, so the execution time is much smaller, and then the frontier grow, and eventually the frontier will start to shrink because you're running out of unvisited nodes, right? So the frontier will then shrink. So for breadth first search, this is a very typical profile of the amount of work that you need to do for each sort of each segment of your execution history. So this is showing that if you use the CPU to handle all these frontier nodes, versus using the GPU to handle, the green is the GPU to handle each of these frontiers, then you have a different time, right? So for small frontiers, you see that the CPUs actually have faster or shorter execution time, right? But then, as soon as the frontiers grow big enough, then the GPU will begin to have shorter execution time, right? And then towards the end, when the frontiers became small enough, then the CPU will begin to have advantage. So this is very consistent with our previous comment about using a small kernel too, right? If if the frontier is small, in a GPU using a small kernel with only 1 block will also be much faster, right? So you don't need to have that much parallelism, but you want to have lower latency and then lower memory access overhead. So part of the reason why the CPU is so fast on these smaller frontiers is that those frontiers will likely fit into the first level cache or at most the second level cache. So for CPUs, when things are fitting into the cache, you're just writing into the cache and reading from the cache, and that's very, very fast, even compared to some the small kernels in the GPU. So when we look at the CPU, GPU, frontier, we can, based on that result, we can just say, okay, if the frontier size is smaller than a certain amount, let's use the CPU, right? And then the frontier size is big enough, let's use the GPU. So this is the coarse grain task, the task collaboration. Because if you have, you look at a task and say, in order to handle this frontier, is a task. Do I give it to the CPU or do I give it to the GPU? And I use the CPU or the GPU for the best fit, right, for that task. So I just test the frontier size and I launch the CPU threads, or if the frontier size is big enough, I launch the kernel. So the interesting part is that if I just use the CPU all the way through, then I have a kernel, I have an execution time. If I use the GPU all the way through, I have an execution time. But if I choose between the two, I can actually do a little bit better than the GPU, okay? Because I'm using the CPU for the smaller frontiers. Unfortunately, this particular way, the benefit is not always great. Because in this particular pattern, the reason why you get a little bit benefit is that you use the CPU for the small frontiers, right? But by definition, the small frontiers will not take a whole lot of execution time anyway. So that's why when you use the right things for those small computation tasks, the benefit by definition will not be great unless during most of the execution time you're handling small frontiers, right? But it's not the case. Like we saw that about maybe less than half, right? About less than half of the time, if you look at about less than half of the frontier, where the CPU will have the clear advantage, right? Clear advantage for handling those frontiers. So if it's no more than half of the frontiers, and each of these frontiers are also smaller, have less amount of work, you cannot expect to have a very big performance improvement. So these are the kind of intuition that you need to begin to build up, right, for these kind of heterogeneous computing systems. Is it really worth it? Is it not worth it? Kind of thing. So it also tells you that the performance can be very fragile if you start to have some overhead. So this is the previous result is based on when you want to launch this kernel to the GPU, you copy from host to device, you launch the kernel, and then you copy the result from device to host. So that was the measurement that we had in the previous slide. Okay, and you can actually use unified memory. So if you use unified memory, you can simply launch the CPU code or the GPU code on that same memory data object. Okay, and then when the GPU executes it, the unified memory will move. The manager will move the data as page faults happen on the GPU and then into the GPU, right? And then when let's say if the previous frontier is generated by the GPU, but then you want to switch to the CPU. During that switch, the CPU will have page faults, and then CPU will pull the data. The unified memory manager will pull the data from the GPU to the CPU. So basically, you trigger page faults during that switch, right? So what you can expect is that in this frontier, so you would start with CPU, okay, and then at some point you have this crossover, right? So you say, okay, the next one I'm going to use the GPU, but then when the GPU kick in that let's say frontier 401, then you will start to have a bunch of page faults, and that's when the data gets pulled into the GPU, into the CPU, the GPU side, and then you will stay on the GPU for all these hundreds of frontiers until you say, oh, the CPU is good, it's good again. So I'm going to switch to the CPU, and then the next couple hundred frontiers will be handled by the CPU. So the page faults don't happen all the time, but it happens during this transition point and this transition point. But this is enough that it can actually cause you performance penalty. So this is the current hardware. When you have in the current generation hardware, just the page faults in those transition points. So this is the CPU, GPU, unified memory, the unified CPU, GPU, unified memory execution, and you can see that those page faults will actually bring the execution time back up. So it's actually better if you just explicitly do this and then copy transfers. Right? The main copy transfer allows you to do better than executing all the frontiers on the GPU alone, right? On the GPU. But as soon as you start to use the unified memory, those extra page faults are going to essentially take away all the benefits by doing the switching. So you're actually going to be better off just do the main copy and then do this. And but it still gives you a slightly better result, okay, a slightly better result than using the CPU alone. Okay, so the benefit is no longer great. Okay, so this is really the frustration, a lot of the frustration of using the current generation unified memory. The page fault overhead is enough that it can wipe away most of these kind of heterogeneous collaborative or selective execution on the device that's the best suited, right, for a particular computation phase for a shared data, right? So that's where a lot of the improvements will need to be in the future. Any questions about this? Yes.
So how is there performance improvement from doing CPU with unified memory versus just the CPU? Like, wouldn't there be some amount of overlap in the uniform measurement?
This is actually a really good point. So, honestly, I think this is probably just a measurement variation. You know, I'm not sure that there's any benefit. They should be slightly slower, right?
Yeah.
Exactly. Okay. So, it's just some summary of what I just said. Okay, so there's one more thing about so what I talked about so far is a coarse-grained collaboration that you can move a task between the CPU and the GPU depending on the data characteristic, right? The bigger frontier moving the GPU, smaller frontier moving the CPU, but the tasks are coarse-grained. That is, entire frontier, right? When you handle that entire frontier, you either have the frontier handled by the CPU or GPU. Okay. But there are also things that are going to be more fine-grained collaboration. That is, you can potentially have a small part of the task to be to be done by the CPU, and then the GPU can take the data from the CPU or vice versa. So we're going to use it actually it's not easy to figure out this without really understanding the computation. So this is the pattern that we have in the chai benchmark suite. It's the Economotion, condensation, and moving object detection. So this is actually a very important application for drones and self-driving cars. Okay. So the issue is this. The issue is when you have some kind of a vehicle or some kind of drone that is flying or moving, and the question is, can you detect moving objects versus the background? Because when you are moving yourself, okay, when you're moving yourself, everything is relatively moving, relative to you, right? But how can you tell that some of the objects are moving? So those are the objects that can potentially run into your course, right? And whereas what are the objects that are really just in the background, stationary, and that they appear to be moving because of your movement, right? And for some of these robots and so on, there's also this kind of a motion compensation issue, because if you have a robot that is doing this, okay, the camera is going to be doing this. So you have these up and down movements, and then so can you tell that these objects are actually the background objects that appear to be moving because your camera is moving versus they're actually moving around, and those are the ones that you need to pay attention, right? So this is what the classical motion compensation computation. So you have sometimes you have these the robots that tend to have these kind of more leg kind of things that would require more of the motion compensation. So the particular method that people use for motion compensation is the popular one is the random sample consensus, or RAMSAC. So basically what it's doing is this. So you have all these potentially moving objects. So these are the kind of the optical flow vectors that you can run a simple optical flow on your video. So then you will say, oh, all these things are moving. Okay, all these things are moving according to the 2 frames, right? Because the motion, the optical flow, motion compensation. Okay. Because the optical flow is kind of, it's a very simple and I would say primitive comparison. You compare these video frames, and then you see, if one object moves in a position in the next frame, right? So then you say, okay, there is a vector. There's a flow vector for the object between these frames. But then, how can you tell that these optical flow vectors are, let's say, because of your own motion or because they are really moving, right? So when they're really moving, we call them fast-moving objects. And then when they appear to be moving because of your motion, then they should be slow motion, slow moving, and also the degree that they move should be very similar. That is, because they are all moving, appear to be moving because of your motion, right? So their movement, according to your camera, should be very similar to each other, right? So the trick is to find the motion vectors that are different, right? That are very different from others, and those are the real motion ones. Does that make sense? So the way to do this, the most popular way is actually a brute force way. So you randomly pick these vectors, okay? You randomly pick these vectors and compare. And if they're the same, then they are likely going to be what? Background. And if they're different, then the faster one will likely be the real moving object. But you do enough samples. So the problem is this. The problem is if you pick two vectors from both from the background, they will be the same. But then if you pick two vectors both from the moving object, they will also be the same, right? So you need to statistically avoid this kind of problem. So you need to make enough samples, and then you need to make sure that you have enough comparisons that in the end you have statistically meaningful representation of the real movement of all these different objects. So this is why it takes a lot of computation to be able to get a reliable estimate of what are the real moving objects. So that's why these things are very suitable for GPUs, because basically you have a huge number of threads, and then each one would pick a random pair, right, and do the comparison, and then contribute to the statistics, and then you have enough of these threads to be able to give you reliable estimate. On the other hand, once you generated some of these things, you're going to have some decisions to make, and these decisions based on statistics tend to be much better done by the CPU because there are a lot of conditionals, and then there are not a whole lot of parallelism. They're based on the statistics that you generate from the first phase, and then you do the decisions. So that's why a good implementation for this kind of method would typically have a CPU component and a GPU component. The GPU component would be doing the statistical sampling and then doing all the comparisons in parallel. And because they are all random, they're all independent of each other. As long as your random variable generator is good, and then you have the CPU to do the kind of the initial assignment and also the statistical analysis. So this is actually one of the benchmarks that we have in the implementation. Unfortunately, what it means is that every thread, after they finish the comparison and the contribution, they generate some results, and then that result needs to be moved to to the other side. And this is done through a fine-grained queue. And these fine-grained queues can be, will be inserted from the source, and then it will consumed by the other device. And these things are implemented by atomic operations, what we call the system atomic operations, because these atomic operations need to be performed by both the CPU and the GPU, right? So if the CPU is the producer, the CPU needs to use the atomic operation to increment the queue tail and put the result into the right location. And the GPU also needs to use the atomic operation to pick up the value, to pick up the entry, and then read the entry, the index, and then read the entry index, and bump let's say, the head pointer, right? So these are the kind of atomic operations that need to be done on both sides. So what this is, in general, only available when both the CPU and the GPU implement the atomic operation in a consistent way. So that's why when you have a NVLink based hardware such as the IBM hardware today, the IBM processor and the GPU can both use the same atomic operation on the shared memory variable, and they will work. But if you use x86, then it becomes very questionable. Okay, so that's why some of the system atomic operations may not even work on the x86 based systems. So if you're interested in some of these, how to implement these fine-grained queues, they are all implemented in the Chai benchmarks, and then Juan Gomez and ETH is now extracting some of these things and then implementing them into libraries, so that the CPU GPU collaborating code can just use the library code to be able to use these atomics and so on properly, and then like the global barriers and so on, so that it's easier to write collaborative code for the CPU and GPU. And so these are the kind of code that you can see. So this is open source, by the way, so you can just go to Chai and then look at any of the code that you like. So if you're thinking about doing some kind of CPU GPU collaboration for the final project, so this will be a good resource for you to look at the code patterns and so on that you might be able to use. And some of these things are non-trivial, so you definitely want to spend a little time to look at them carefully. Okay? Okay. Good. So that's the end of the lecture sequence. But, oh yes.
I have a question about the queues. Are these typically just single producer, single consumer, or?
No, not necessarily. A lot of these times, it doesn't matter which thread picks up which one.
Okay.
Yeah.
So it's just something has to pick it up.
Yeah, so that you have better load balance.
Yeah.
Otherwise, you need to have a lot of queues. So that's the problem.
Yeah.
Right? So a lot of times it's actually multiple producer, multiple consumer, and but you also need to make sure that you don't have very, very heavy collision. So that's why you'll have multiple queues simply because you want to have higher throughput.
Throughput, right?
Yeah. So that's the typical scenario. Bert.
Yes.
So tell everyone about MP.
Okay, we're working on the merge sort MP with the TA at the moment, and we'll let you know. We'll release the MP as soon as possible.
Hopefully.
Hopefully today.
Okay, that's a key word I wanted to hear. Okay. Okay. So questions or any questions about the final project so far? Yes.
I just have a question about the BFS.
Yeah.
Again, maybe I'm not understanding it, but why can't you just put C threads and that's it? Why do you have
Yeah,
to
yeah,
sync
yeah.
threads?
This is okay. So let me draw the picture. So let's say we generate the frontier, okay? So the frontier is this, right? So this is, you finish generating the frontier, and then in the next iteration, what happens is you have threads to pick up these nodes and visit their neighboring nodes, right? So let's say, let's assume just 1, 2, 3, 4. Let's say each thread block, let's say 4 threads. Okay, make it small. And then the next thread block will pick up these, right? So what happens is that, let's say each thread block has 4 threads and each one is processing 1 frontier node. And after they finish, so the way we do this is that let's say if we have 2 thread blocks, then the 2 thread blocks will finish this one, and then the threads will advance here and advance here, and then finish the computation.
So basically, the frontier is larger than the size of the number of your threads.
Yeah, because frontier grows and shrinks. You don't know exactly how many, right? So this is the reason why we have that for loop. The for loop will say, okay, all the threads in the grid, so in this case, two thread blocks, 4 threads each, consume the first section of your frontier. And then the for loop will take them to the next one, right? The next one. Now, at some point, one of the thread blocks will finish, right? One of the thread blocks will finish. So then it will go, it will go into the sync thread, right, for the thread block. But you have to make sure that those threads don't go into the next iteration until the other thread block also finishes. Because you have to, everyone has to wait until all the frontier nodes are completed before you go to the next, process the next frontier. Otherwise, you will end up generating nodes too early, right? So that's where you need to make sure that you have a barrier across the thread blocks. Sync threads only work within the thread block.